Okay, so we're starting in a minute or two. I'm just gonna briefly say hello to everybody. So hi, my name is Ben. I'm gonna be one of the speakers today. I teach the CS 8.4 and 8.5 classes at times. I've taught CS 8.2 here at KTBYTE, and those are our statistical and machine learning classes. Additionally, we have Pratik.
Hi, my name is Pratik. I'm a rising junior at Acton Boxborough Regional High School. It's a high school in the area, and I've been taking KTBYTE classes for the past 4 years, I want to say. So I've done everything from basic CS, like introductory Java lessons, all the way to machine learning CS 85 lessons.
Yep. So we're going to talk about a lot of different things. One of the things is what is AI and what are some of its applications? What is its history? Pratik, you're going to talk a little bit about some of your past projects and experience. I think you've done like a couple
Yeah,
machine learning projects, right? And you're also doing an internship right now.
yeah, I'm doing an internship at Dana-Farber Cancer Institute this summer. So it's mainly to do with the same kind of things like machine learning and deep learning. So yeah,
Yep.
it's relevant.
So we'll talk a little bit about those experiences and also kind of like what the material of coursework is. Okay, so I guess we'll get started. Okay, cool. So welcome everybody. Today we're going to talk about AI. AI is a very popular field right now and popular both for academic researchers, people in industry, and sometimes for students. And it's a complicated field because no one's not exactly sure what AI is. Obviously, a lot of people say AI is demonstrating some kind of intelligence by computer. And the two kind of buzzwordy terms these days are machine learning, and that is using a computer to learn from information, and deep learning, which are specifically neural networks that are consisting of many layers of neurons in the computer that have similarities to our brain, but allow the computers to make predictions. And so a lot of AI these days is being able to take an input, like a picture of a cat or a dog, and tell you whether it's a cat or it's a dog. Or Pratik, what kind of predictions are you trying to make, for example, in some of your projects?
So some of the projects that I'm doing are mainly like have like a medical focus, like telling whether like a tumor or an image of a tumor is benign or malignant, or saying whether it's harmful, or like predicting with features of cancerous images basically. And this can be
Yeah,
for breast cancer, lung cancer, anything where there's like x-rays or images involved.
yeah, and I think you did like a couple science fair projects. One was using a neural network. One was not even using a neural network, using a more traditional um, algorithm. And typically when people talk machine learning or deep learning, they're talking about two classes of problems. One, which is called unsupervised learning, which is trying to categorize things that are different from each other. And another, which is called supervised learning, which means given some training data, which has, for example, a picture of a cat, and you tell the computer this is a cat, and here's a picture of a dog, and you tell the computer this is a dog. Next time you give it an unknown picture and you ask the computer, is this a cat? Or is this a dog, right? And can you kind of use that analogy, Pratik, to describe how this might apply to, for example, cancer research?
Yeah, so going along with that analogy, like if you have a data set consisting of, let's say, all like mammograms or like x-rays of breast cancers, you can have like a set of the data be benign tumors or tumors that are harmless, as well as a set of malignant tumors or tumors that are harmful to the body. And what in this case you do is you feed the neural network or the machine learning algorithm the data set with both sets of benign and malignant images, and you ask it to say, like, if I give you like an unknown image or like a new image of a person that has potentially breast cancer, could you tell me like if it's benign or a malignant tumor, so whether it's harmful or harmless? And this is for totally new data that it hasn't seen before. So that's that's basically a connection.
Yeah, and actually for the first part of our talk, we're going to be talking a little bit about the history of artificial intelligence, because I think a lot of people see these applications towards cancer research and say, wow, that's amazing. Or we look at, for example, the self-driving cars that are coming out, or like Alexa being able to understand your voice when you're talking to a device. And I think there's a lot of promise in this field, but it's also interesting to see where we came from. So we're going to go start with a little bit of history first before we dive too much into applications. Um, and again, for those people who are new, you guys can always chat in the answer and question area if you have any questions for us. But AI is a pretty old field, actually, dating back even in a computer sense back to the 50s, 60s, and 70s. Back then, there were programs that, for example, could play checkers, and it might, for example, look to see whether there's a piece that you can jump over to to take over some kind of piece in checkers. And a lot of these used if statements and logic, the kind of programming that a lot of our first or second year programmers, sometimes our 9-year and 10-year-olds, they learned. But back in the 50s and 60s, this was very revolutionary, because prior to that, computers couldn't really make decisions if you had a workstation in an office or at a research center. You could suddenly allow computers to behave in some kind of logical way. For example, one popular program in 1965 called ELIZA was a program that pretended to be a psychotherapist, someone who you talk to if you have like depression or something like that. And how ELIZA worked is, if you typed a message like, oh, I'm very sad, ELIZA would notice the word sad, and ELIZA would speak back and she would say, oh, tell me a little bit more about why you're sad, or when did you start feeling sad, or whatever. And so there also were programs like in 1979 that allowed you to see if you had a disease. And the way that worked is, if you typed like, oh, I have a fever, it would find all articles that, or all diseases that had the keyword fever in it. And I think for anybody who grew up in the last 20 or 30 years, 40 years, this seems very easy, very obvious, not artificial intelligence. And I think that's going to be one of the big themes of today's talk, is that throughout the decades and even now, people have said, wow, that's amazing. That's like more intelligent than any computer I've ever seen before. This computer is going to become almost sentient, almost replacing humans. And what we find time and time again over the decades is that computers have been doing these really amazing things, but every time something new comes out, that thing over time we kind of get accustomed to, and we move on to the next big thing. So in the 50s, 60s, and early 70s were these logic-based AI programs that used if statements to be able to determine whether or not something needed to be done or some behavior needed to be enacted. And I'm going to segue now out of the 50s, 60s, 70s. And there was kind of like a little AI winter, and people said, oh no, computers, we thought they were going to be amazing in the 50s, but turns out all they can do is play very simple games of checkers. They could never beat a human in checkers, right? And suddenly in the 90s, and this is when I was growing up, um, computers could be humans in checkers. So in 1994, you had some of the first programs that could defeat humans in checkers. And then by 1996 and 7, that's when this program called Deep Blue came out. I think a lot of us who are over the age of like 30 remember this pretty vividly in the news. Garry Kasparov, this very famous chess player from Russia, was defeated by he was the world champion at the time, was defeated by the IBM Deep Blue computer. And at the time, people said, wow, computers are never going to be able to play chess, because chess has so many possible combinations of moves, you can't evaluate every single possible combination. And so in the 90s, there was these new ideas, these data structures that finally computers could run, because mainframe computers were getting more powerful. These data structures called like trees, graphs, and matrices, things that you learn now if in your basic CS course. We no longer consider this as artificial intelligence. And very quickly in 1994, 96, 97, they beat humans at checkers, chess, Othello, other kinds of games. And so it was pretty amazing, because suddenly we thought, wow, computers will beat humans at any kind of game. And it won't be long before things that are very similar to games, maybe like diagnosing a disease, maybe that's like a game, computers might be better than humans at. And This is actually not true, obviously. It didn't happen in the 90s, but you can see that a lot of these concepts, in the case of the previous slide, which are like logic, they came out in the 1800s, but became popularized in the 1950s. People thought it was AI. And the concepts such as trees, graphs, and matrices, things that were really popularized in the early 1900s, and mid 1900s, that's what kind of became AI in the late 90s. Even back then in the 70s, 80s, we had these concepts such as neural networks and backpropagation. And so it's interesting to see this progress because once we hit the 90s, and you'll see later the 2000s, people started thinking, wow, it's going to be these support vector machines, these statistical approaches that are able to sometimes do character recognition, or even neural networks, deep neural networks that became popular in 2000, 2001, 2010, 2011, 2012. Those will become really good. And so the most recent trend is these deep neural networks. You can see this chart on the right. It's part of an image recognition contest called the ILS VRC contest. And you have this red bar, which is the error. You can see the error in 2010 was around 28%. And by 2014, it dropped dramatically to 7%, which means the accuracy rate was 93%. And what happened is from 2010 to 2014, the number of people doing this contest, mostly universities, using GPUs, they increased a lot. So a lot of people started using these gaming processors because people played a lot of video games in the 90s and 2000s. So we have this new consumer hardware. And so what that means is that this technology, which included vectorization and included these neural networks that came about in the 1970s, it became really useful in the 2000s and 2010s. And so right now, when people say artificial intelligence, usually they're talking about deep learning. They're talking about deep neural networks. But this chart is very important, this history, because it means that when you're learning machine learning or artificial intelligence, it depends on what area of history you're focused on. It impacts what kind of actual technologies, techniques you'll learn. And so it's very likely that after another 10 years or another 15, 20 years, we'll see AI go through like another winter and we'll think, oh, AI is dead. Deep neural networks, maybe they're not that good. And we will kind of move on to kind of a next era by which some new technology is implemented. And another theme that you should take from this is that with every single change in artificial intelligence, you saw corresponding changes in hardware. In the beginning, it was mainframe computers, then personal and distributed computers, and now graphics processing units. And so that may be the case with neural networks as well. So nowadays, with these new GPU-based neural networks, computers can recognize images, they can recognize pedestrians in the streets, do face recognition, do language and sentiment analysis, do radiology, like Pratik, you were talking about, and beat humans at games such as AlphaGo, which is playing the game of Go. Or recently, for example, there are some research papers that are just coming out where computers are trying to play these video games such as this thing called League of Legends. And so we have all these new papers coming out. And so we're going to talk a little bit about kind of what are the cutting edge applications. So we talked about text recognition. That really became popular in the 90s, but now it's very, very good. You know, I can remember when you could finally get Google Translate, you can point at some text, it'll translate to something else. Object classification, face recognition, translation, self-driving cars. And you can notice, I'm sure when you're using these devices, a lot of people have used text recognition, that there's still edge cases that the computers aren't that great at. And so what we find with many of these technologies is that it's easy to get the technology to maybe a 90%, 95% accuracy, but oftentimes the last 5% is very, very difficult. For example, in the case of text recognition, a lot of it is the context, the culture, or the history, or the current events that the text is based off of. And when it comes to self-driving cars, a lot of it is based off what predicted human behavior the other drivers or people on the road or pedestrians are doing, or the local regulations and local roads. And so a lot of these things are still not there yet, but you can see that these applications are coming out. Um, Other popular topics that have been attacked by the neural networks recently have been looking at biological, chemical, or physical simulations, or biological, chemical, or physical data. So Pratik, you mentioned mammograms, you mentioned cancer.
Yep.
Even when you're not detecting cancer, if you want to just tell whether a cell is dividing, if you want to detect cells undergoing mitosis versus those that are not undergoing mitosis. Previously, like my first internship back when I was your age, Pratik, I was counting cells originally using like a clicker machine. It was really painful. And then
Yeah.
eventually tried to use a program that would find color barriers and use like flood fill to detect like barriers in cells. It was very hard. And nowadays that kind of algorithm is very easy.
Also,
Um,
in the sorry for interrupting, but in the science field as well, I was reading this paper that deep learning can be used for like optimization with like the GAN stuff that's coming out, like the generative networks. Like you can actually make the most optimal thing. Like you can use that in engineering. You can also use that to make the most optimal drug. So using deep learning is also coming up in like the optimization field as well.
Absolutely, absolutely. You mentioned drugs. This next thing is toxicity predictions of chemicals, and there's a good number of pharmaceutical applications these days by which, rather than starting with clinical trials, you'll start with a database technique where they will take some kind of compound and run it against other similar compounds to try to estimate what its behavior might be like, both in vivo, in vitro. And so previously, these kinds of wet lab simulations might be very expensive, but now when you have a data-driven technique, it might not be perfectly accurate, but oftentimes it narrows the search space, so you don't have to do as much stuff in the lab as you might have had to do before. And similarly with physical applications, before you had very complicated programs to simulate stress and strain of bridges or simulate, in this case, fluids. And recently, we've been able to create computer programs that say, okay, by looking at all of these previous fluid simulations, can you estimate what future fluid simulations will look like? And they can try to derive some of the rules just by watching how things behave. And so definitely deep learning is impacting science as it is right now. But we also see it not just in the sciences, but in a lot of regular consumer kind of applications. So some of these are really cool. Some of these are pretty scary. So you see it in image coloring. So if you want to take a picture and make it a certain color, or you can even, for example, take a grayscale picture and have the computer guess what the color should be. And so these are examples of grayscale pictures that the computer colored, and it does a remarkably good job. Okay, so the right side is the true color, which the model never saw. The output is the middle image, and so you can see from this image that like it figures out that grass is green, figures out that certain animals are different colors than the grass, all these kinds of things. Right? And also, if you just want to change a picture from one color to another, that's being made a lot easier. Similarly, you can, or not similarly, but also you can, for example, take a picture, in this case, the Eiffel Tower, and have a program try to detect where you are in the world. And so this photo geolocation stuff, very useful for a lot of these like imaging applications, like for example, Instagram or Facebook. You take a picture and they'll automatically be able to determine from the foliage, from the architecture, from the kind of people, what they're wearing, the clothing, the fashion, the image, that will try to estimate the location on the world. And previously, this would be extremely difficult for a regular algorithm. Okay, so you can see applied towards consumer applications, artistic applications. A lot of things that also we thought was really impossible a short time ago is now possible. One is like this picture here, where you take a picture, cut off a piece of it, and try to tell the algorithm to fill in the blank. There's a really impressive video by NVIDIA that came out just in the last 6 months in April. It's called AI Constructs Photo with Realistic Results. And you can see people drawing these white areas and the algorithm on the right side filling in those areas. So for example, we have this bridge in the picture and the algorithm gets rid of the bridge and fills it in with a realistic rocky landscape to fit in with this landscape here. And you can even get rid of this enclosure. You can do this in rooms. You can do this in with faces. You can see here the face on the right. It looks kind of wrong, but that's because the eyes were generated by the algorithm. And so a lot of these applications can be useful for the arts. And while previously, if you used Photoshop, you might be like able to resize things, make, for example, objects look smaller or bigger. Now suddenly you can add realistic elements to an image without having to draw them painstakingly or copy them from one image to another. And so these are really powerful artistic and graphical applications of machine learning. Here on the right side, we have some image captioning algorithms, which allow you to, for example, take an image and I can't actually find the exact example paper off the top of my head right here, but maybe it's this. Oh yeah, here's an image captioning paper. So you can take an image, determine portions of it and label them with text. Or you also have these super resolution algorithms. So for example, this one is a super resolution algorithm. On the left side, you have the original picture. On the middle side, you have the picture that was fed to the algorithm. And on the right side, you have the picture that the algorithm produced. So it's able to take a low resolution image and create a high resolution image. I remember when I was a kid watching like CSI, NCIS, or some kind of like crime show, and they would like have a picture, a video of some like zoomed in, like grainy image, be like enhance. Oh, now we know what the driver's like license
Yeah.
plate is. Now we can chase him. And at the time I was like, that's impossible. I'm a programmer. I know that's impossible. And now, you know what? They can do it. But the caveat is it might not be the right license plate number because the computer is trying to just guess and fill in the blanks. So what computers can do now is they can fill in the blanks and make things that can trick a human, but it may not be correct, right? Like if you blotched out her nose and she used to have a dimple or a freckle, it might not be there in the reconstructed image. And so a lot of these algorithms are very powerful because they can do things that are indistinguishable to human labelers. A couple more papers before we move on. One is image synthesis. So we have here this image. You can see the colored one, which is called a semantic map. A human draws this and says, I want the road here, I want a car here, I want trees here, I want pedestrians here. And this other image, which looks like it's a photograph, that's actually generated by the algorithm. So the algorithm will be able to create visual elements from these semantic maps. And currently, for example, if you want to make a video game, you have to import lots of complicated textures. You have to render all of these images and try to make it look realistic. It looks like these new algorithms may enable you to make a game that has all sorts of cool elements without having to even program any of the models they use in the game. These algorithms allow you to, for example, change faces. There's some very scary videos of people making Barack Obama or Donald Trump say something they didn't actually say because the algorithm can simulate their mouth movements, simulate their voices, scary stuff. But there's also algorithms being released to try to detect these. You can have algorithms that determine what's making a sound. If they can figure out that it's a person making a sound and it's coming out of their mouth, or it's a violin, or it's a cat, right? They can figure out from video what things are making what sounds. And there are also pictures that are able to, as you can say, completely change scenes and try to fill in not just like a picture of a face, but take in this bottom right picture, a picture of like a bay and be able to like construct boats or fill in the rest of the bay. So a lot of these cool image-based technologies that weren't even imaginable a short amount of time ago. Okay, so I'll pause just for a second. If anyone has any questions, you can again put it into the question functionality in the GoToWebinar. I think what's also amazing about these, in case no one has any questions, I will.
Oh, there's one question.
There we go.
Yeah.
Can you code AI in Python? Okay, yeah, go ahead, Pratik.
Okay, so you can code AI in any language you want. Whether it's easier to do it in Java or Python, I would choose Python because Python gives you like a better framework to do AI. Some of the packages that I use, like Keras, is specifically like designed to be used in Python, and it's very easy to use in Python because you don't have to pre-code all the functions yourself. So all you have to do is call the pre-coded functions for you, and just organize them in whatever way you want. So it's way easier to do it in Python.
Mhm.
And yeah, Python is the preferred language in AI, but yeah, Usico prefers Java because it's like more algorithm based. It's not machine learning based. It's more of like, um, it's more of can you create your own algorithm to solve like a real world problem. So that's why
Yeah,
they use Java there.
there's a bit of history here in the sense that like a lot of the academic researchers that are working on machine learning right now are building their libraries in Python. And so because it's a relatively new field, there isn't great library support in every single language. This is a very different from if you wanted to, for example, make a program that converted uh, a like one type of image to another type of image, like a BMP to a PNG or something like that. That kind of library you can easily find in pretty much every single modern language. But yeah, Pratik is right. Like right now, the Keras, TensorFlow, Theano, uh, those are just like way easier to use in Python than specifically deep learning 4J, which is the most popular Java-based framework. Yeah. Um, Anything else you want to say about that, Pratik?
No, I didn't know deep learning for J existed, but
Or I actually don't know if I even said it right. Deep learning Java. I think it's deep learning 4J. It's deep learning 4J. Yeah.
yeah,
And
I've mainly used it for Python, but yeah.
that doesn't mean that if you want to use a specific language, you can't do machine learning. But that just means that it might be a lot hard to get
Yeah.
started, or that you'll have a lot more trouble finding right examples that you can use, or it might be more difficult getting it to run on your computers. Can you speak a little bit about hardware, maybe, Pratik, for a second? Like, because you've been doing some research in different environments. Like, um, how does hardware affect how you do machine learning?
So hardware mainly affects the amount of time that your algorithm might take to run. So right now, the hardware that I'm using is connected to like a virtual server. So what I'm using is a pretty good graphics card. It's the GTX 1080 Ti, I want to say. Yeah, and we also have a Titan X here. So those are really two really good GPUs that I'm using. And so compared to that, if you were using like a GTX, let's say 960 or a 970 that you have in your house, the only thing that I think gets affected is the amount of time that your algorithm will take to run. So let's say with a GTX 1080, you could probably run a really big deep neural network in about 2 to 3 hours, while with um, a not so good graphics card, it would take much longer to run. So
Yeah,
it mainly affects running times of your algorithms.
yeah. And also, one thing Pratik didn't mention is if you don't have a GPU, it could take a really long time to
Yeah,
run. So if you're running on like your thin and light ultrabook light laptop or something like that, your like MacBook Air or something like that, it's not going to take 2 hours. It's going to take like 2 weeks.
yeah.
So so yeah. Okay. But yeah, that was a great question, Howard. So feel free to the rest of you if you have any questions to shoot them over. Okay. Um, a common question we get now that we've seen a lot of these applications is, wow, AI is doing all these amazing things. It's replacing truck drivers. It's replacing doctors. It's replacing graphic designers. It's replacing paralegals. Huh? Yeah. And so is it true that AI is going to destroy all these jobs? Um, and it's a complicated question because I think most people who are researchers don't think too much about the economic implications. But I think most people who are studying the economic implications would say that it's not going to necessarily destroy as many jobs as the newspapers or media outlets might say. The most likely biggest change is it's going to change a lot of jobs. The analogy being if you were a graphic designer in the 1980s and 90s and you didn't use Photoshop, that's okay. But if you're a graphic designer now and you don't use Photoshop, Illustrator, Figma, whatever, your life is going to be a lot more difficult. In the future, there may be truck drivers, but maybe more of their responsibility is going to be the regulatory, the licensing, the bureaucratic, and also the managing of several trucks rather than just one single truck. A doctor may spend less time looking at skimming through many mammograms, many x-rays, but maybe they would focus on a few where the computer is not so sure about it. And also, of course, doctors have a lot of other, even radiologists have a lot of other work besides just determining whether it might be benign or malignant, right? So a lot of this is going to shift work from something which previously was a recognition problem, and humans are good at recognition problems, but now computers are also good at recognition problems, to maybe artistic or a communication or a creative or a thing that requires synthesis or balancing different factors that influence different kinds of stakeholders, like a patient or other cars on the road. And so these things that computers still can't do, and most researchers don't think that computers are going to be doing these higher level tasks in the next 10 to 20 years. And so this means that some jobs will be changed. Maybe a small number of jobs will, and not small like one or two, but definitely many, but small on the national scale. A small percentage is going to be destroyed, and also a small percentage will be created out of thin air. Maybe there will be new people who work specifically on optimizing, tailoring, and understanding these algorithms. Because some of these algorithms, unfortunately, are also black box algorithms where now it's great that the computer can make a decision, but oftentimes the computer cannot tell you why it made a decision. So yeah, okay. So that's one question that we had asked beforehand. And another common question we have is what should students do and how should they learn, given that these are kind of the big trends? Should I be focusing as a student on learning one specific neural network, or should I be learning like Python, or should I be learning core computer science? I'll speak first to kind of KTBYTE's general experience, and then Pratik, maybe you can talk about it afterwards. In general, we find that the most important thing is for students to have a really good core computer science experience, and that's a prerequisite to being effective at machine learning. If you learn one specific algorithm or you learn one specific tool, that might make you have a definite edge in the short term, maybe like 1 or 2 years, as people learn how to apply that tool, because you might be able to hit on applications that other people haven't. But over time, these tools will get more and more common, and like any tool, they change over time, you know. And so just like computer science hasn't really changed necessarily for dozens of years, but operating systems and graphics and image editors do change. Similarly, a lot of the statistical and data structures technologies are going to really stay very similar, but what particular variant of a neural network might change, or what particular library they use to implement a neural network might change from a year-to-year basis. And so that means when students are learning, they should be focusing on CS. They should be focusing also on research skills. So a lot of the problems that students have when they're doing this kind of work is that it's very different from, like you mentioned, Pratik, earlier, like the USA Computing Olympiad or like school AP Computer Science, because there's no right answer. Like oftentimes when you're doing research, it's actually hard to even know what questions you should be asking, forget finding the answers to the questions. And it's really challenging to budget your time, because if you have 5 or 6 questions that you might be able to ask and you can only answer 3 of them, then which ones should you focus on trying to answer, right? And so students are going to learn time management, how to do things in parallel, how to communicate their findings, how to use resources and other people's experience and other students and advisors to be able to plan their time, and also to work around deadlines and institutions if they're submitting these projects or working towards a research project. So like when we had one student tried to distinguish between Harry Potter books and Harry Potter fan fiction. This student, she actually had like 4 or 5 ideas originally, right? And this was just one of the ideas that it turned out in an early version of her program that she was able to get good results on. And so she was able to like dive down that path. But the process of arriving at that cool project, you actually, if you just saw our paper, you don't see 90% of the work. And I think probably Pratik, you can speak more to this than I can because you've been doing a lot of that recently. Well, what's your
Yeah.
experience been like?
Okay. So as Ben mentioned, like core CS is very important, because although like neural networks and deep learning, like the ideas and the algorithms, they pretty much change every single week, and like you need to like read the newest paper to keep in touch with that. Like the core part of machine learning and deep learning is knowing how to like work with data and knowing how to um, change the data in order to meet like the requirements that you have, and the majority of that is wrapped around core CS, like um like data structures and algorithms like that. So it's important to know core CS before you like kind of delve into machine learning. And like, what was the second part of your question, Ben? Like
Like, what was the experience managing your time, and like what was surprising when you were doing research? Because I think a lot of people when they start research are like, I'm gonna build this model and then I'm gonna like discover this really amazing thing, and
yeah.
it's not like that at all.
Okay, so yeah, one really important thing in research is that the first kind of thought you have will never really be the project that you have at the end. Like many times, like the project that you come out of, like that comes out at the end, will be wildly different, or even like the opposite of the thought you had at the very beginning. So like it's a very fluid process. It goes through many changes, and depending on what problems you have or what roadblocks you hit, you'll need to make changes and adjustments in your research question as well as the methods that you're pursuing, in order to get a feasible project at the end. And many times it might not even be like the project that you want, but it's still important to go through the process and keep building, because it is a long process. It's not going to take 2 weeks to come up with a novel algorithm that suddenly cures cancer. But yeah, it's a very fluid process, and you just need to be prepared to go through it. And you need to be prepared for all the roadblocks and all of the challenges that you might face.
Yeah. So I think, did you take 82 with us, Pratik?
Yeah, I took 82, 84, and 85. So like 82, it really gave me like kind of like a mathematical understanding of what goes behind machine learning, because I think that's important, because before you delve into just like these functions, these pre-coded functions, you need to actually kind of learn what they do. And sometimes in CS82, like you needed to know like a little bit amount of like calculus to understand what was going on. So that was kind of hard to grasp at first, but once I saw the application in 84, I saw where the kind of like the calculus was coming into picture. And I of course had to do some research on my own, but 82 mainly gives you a good like mathematical grasp of what's going on in machine learning before you go to 84, where we do purely example based learning.
I do want to add a caveat that we don't require students to know calculus for any of these
Yeah,
classes.
yeah.
And then what was your experience in 84 and 85 like, I guess?
So 84 was straight diving into deep learning and neural networks and seeing how we can implement them, and using them to do like regression tasks, playing games, classifying objects. So in 82 we did a lot of machine learning algorithms like linear regression, naive Bayes, and things like that. But deep learning is mainly focused on neural networks, and working with Python to create neural networks. And at the end of 84, you do like a small research project, but it's not like the intensity that it is in CS 85, where you solely focus on your own research project the entire time. So my project in 84 was something to do with poker hands. It was like predicting what kind of cards you need for a poker hand, given the cards in the deck or something like that. I spent like 2 or 3 weeks on it, because it was at the end. So yeah, that was a little bit that was the project in 84, but the project in 85 was a lot more deeper and delving into the depths of machine learning and seeing what I could do to kind of find a novel
That was
application
that was
for
your
deep learning.
mammogram
Yeah, that was
project.
my mammogram project. It was basically um, using image augmentation to efficiently classify mammogram images or like breast cancer images using deep learning. So that was a very um, deep, in-depth project. Yeah, in-depth project that took the entirety of the semester,
Mhm.
maybe multiple semesters as well. Yeah.
Yeah, and before we leave the slide, I do also want to talk about why this is a research track versus like I think a lot of the other classes, like our core classes, a lot of the projects are games or apps, so it feels like an engineering track, and a lot of the USICO problems are algorithmic problem solving, so it's very much like a contest. So the style is very different because when you're doing a software engineering project, if it's a small project, then it's very self-contained. But if it's a large project, you're learning a lot of software engineering tools. And like, for example, you learn on how to deal with a big code base or use version control to share code with other people or whatever. And then if you're doing the USAC Computing Olympiad, which is a different thing as well, you're focusing on those algorithms, how to solve them in the quickest amount of time, how to prepare your code so that you're ready to dive in during the contest. While here, it's a completely different feel again, because these machine learning classes, they're long projects. While so long that maybe more than a year that you're working on them, where the project's changing from week to week basis. And so when students ask us like, should we take these machine learning classes, I oftentimes ask them what kind of personality they are. If they like to see a result immediately and have that work, then usually these are not very good classes for them, because that means you're going to be disappointed many
Yeah,
times.
and I also want to add that I was also one of these kids initially. Like I like to see a result immediately. That's why I did USICO, because for the first like at least the last two years ago I was doing USICO like very seriously, because USICO, how it works is like it grades your code in an instant and tells you whether you're right or wrong. So it's kind of like an instant gratification kind of thing. But like through this process, I realized that research is not it's never a one like you do something in like 1 second and it gives you the right answer. Like it's a very fluid process that you need to go through the like sometimes you just need to go through the motions, um, and it takes a very long time to get a result if you get a result.
Yeah,
So
and so it is a research process. That being said, the achievements are pretty cool. So like we have a lot of the students who take their academic papers that they produce in A4 and A5 and submit them to a science fair. And I guess Pradeep, you can speak a little bit to about that experience as well. Like, what's the difference between preparing for a science fair versus actually working on machine learning and working on your project? Like there was like the paper and like the presentation part. Like what was that experience like as
yeah,
well?
so preparing for the science fair actually took a little bit longer than doing the project itself. So yeah, I think the entire timeline was from last summer, starting at like August timeframe was when I was thinking about what I was going to do to my for my project, all the way up to March for the regionals. So from about August to October or November, was actually doing my project, and then from December all the way to March was cleaning stuff up, writing my paper, making my poster, preparing a presentation, thinking. And for these science fairs, it's not really about presenting your work. It's about selling your work in a way that will appeal to a population that doesn't really understand much about deep learning, because deep learning is a very relatively new field in even AI and machine learning. So many people won't really know the specifics or know what's going on in deep learning. So you really have to make it so that they can understand, as well as take a very complicated topic such as your project and make it sellable in a way that people can understand and appreciate the work you've done over a period of, let's say, 4 or 5 months. So in the science fair that I did first was not really a deep neural network or a machine learning or like a deep machine learning algorithm. It was it was concerning like a k nearest neighbors algorithm, which I really coded it in Java, so it wasn't using any deep statistical packages. It was to do with predicting a point of muscle fatigue, um,
Hmm.
using a k nearest neighbors algorithm. So that actually got me to the regional and state science fair this year, as well as last year, as well as a national science fair this year. And so this year was actually my project regarding mammograms and breast cancer. And I haven't applied it to the National Science Fair yet because the deadline for that already passed, but I'll do that next year. But this one actually took me to the regional and the state level science fair.
Yeah. Um, and one thing I forgot to mention is that when you're doing a lot of this work, besides the model part and the presentation part, there was also a lot of systems you had to learn, right?
Yeah.
Like a lot of like tool learning. Can you talk briefly about that?
Yeah, so part of the tools you had to learn, one, I had to learn an entirely new programming language because I'd mainly worked with Java before, so switching to Python was kind of a jump. But mainly like the functions are the same, and the packages, whether you're using them in Java or Python, are totally new and something you have to understand at like the math level first. So using the Keras packages, with once I got over the learning curve, it was pretty easy to implement them. I also had to learn how to use the virtual machine that we have here at KTBYTE, to log into the virtual machine, as well as R to parse through my data, augment my data, clean it up, do the basic janitor work.
There's a lot
Um,
of Linux involved
yeah,
in doing.
Linux as well.
Yeah.
Yeah. So you have to learn, there's a kind of a learning curve associated with like systems, processing language, programming languages. But once you get over that, it's fairly straightforward. I mean, not straightforward, but it's fairly easy to get into the machine learning part or the deep learning part of it.
Mhm. We had a couple questions. One from Howard: how long will it take to finish A2, A4, A5? I think most students do A2 in one semester and A4 in one semester. Some students will spend 2, 3 semesters on A5 because A5 is our kind of like independent study with some tutoring and with some kind of system support kind of track. So 8.5 is unique every single time you take it. It's not, there is no curriculum. While
Yeah.
A2 and A4, there is a curriculum. So usually you just take it for one semester each.
Yeah, and
Um,
8.5, it's a class where you basically take it to depending on how much you want to get out of it. So so like if you want to do science fairs for like 2 or 3 years, then you would take 8.5 for a lot longer than one semester. Whereas for 8.2 and 8.4, there's like a curriculum, and once you feel like you've understood the material, then you transition to 8.5. So I started 8.2 when um I was like, I think the middle of last year or the year before I started A2, and A2 and A4 I finished in about half a year, maybe 3/4 of a year, and then 8.5 I've been doing since the beginning of last year. So
Yep. I'm afraid one of the questions is from Reuven. I might have pronounced your name wrong. But the question was, can you also talk about fundamentals in CS classes? I'm afraid we're going to skip that for today's talk, but you can contact us afterwards because we're going to try to limit this talk to the AI classes that we have circled here. But we would be happy to talk to you afterwards about that. Um, so in kind of a couple slides of summary, why you should learn machine learning or why you might not want to learn machine learning. So if you like research, you can definitely do it. And if you do want to learn AI, we say just not to focus just on kind of the most recent models and kind of what the most recent fad is in the last year or two. And that means all the things that Pratik was talking about. And also to pace yourself a little bit. We do recommend that students plan on doing the high level classes by their sophomore or at most junior year of high school, because you start getting pretty busy by your junior year, which means that we like students who to try this to try entering the track in their 8th and 9th grade. If they want to do a science fair project, it's good if you start 8-2 when you're like a 9th grader, or like are planning to take 9-2 while you're in 9th grade. That way you have ample time to do these kind of long 1-year projects while not having that compete with your SATs, other APs, and college applications, which can be pretty strenuous. And so, yeah, that's like the brunt of the talk. And I guess, Pratik, now that we've gone through this talk, can you talk a bit about like what you're looking forward to? I know you're planning on you're doing, like you said, you're doing an internship at the Dana-Farber Institute, and like now that you've learned these skills, what do you plan on doing them? Why you like research so much? And is this something you're going to think about doing in college or afterwards? Or maybe you can speak a little bit to that.
Yeah, so the main reason I enjoy research is because there's no kind of deadline to finish research. I mean, there will be deadlines based on when you enter like a science fair or a competition, but there's no real like pressing deadline to finish research by, let's say, like next week or the week before, like you have school assignments. Like you can spend as much time as you want on it, and like the finished product is entirely based on how much work you put in, as well as how much you want to gain out of the project itself. So in college, like I definitely want to do something with deep learning and AI, but as Ben said, you have to go through like a computer science, core computer science track first before you want to specialize into different areas of AI and machine learning. So yeah, with this internship, I think it really helps me become like an independent researcher, and it also helps me like get the skills that I need for college, in like a university setting, that will help me kind of that will help me kind of specialize in this track as I go forward. So
We had one parent ask if you could mention which specific science fairs you applied to.
okay, so it depends mainly on the region that you're in. So since I'm in Massachusetts, I entered the Mass State Science Fair. Based on your region, there will be a bunch of science fairs that you can attend. Another science fair that I did was the Junior Science and Humanities Symposium. So it's a national science fair, but the region that I did it in, it's the JA.
Yeah, I
Sorry. Yeah.
junior.
So So here it's based in BU, Boston University, but it's a military kind of funded science fair. The Department of Defense actually funds it. So nationals this year was in Washington D.C. Yeah, New England Southern JSHS. But it changes every year. It's entirely based on where the Department of Defense wants to hold it. So next year it's in Las Vegas. So depending on where you go, your region, it'll vary from there. So those are the two science fairs I've entered in. There are a bunch of research programs that you can apply to, like the Davidson Research Institute program. There's also
Broadcom.
yeah, Broadcom is one. I think that's only for middle schoolers though. I might be wrong. But there's also Stony Brook. That's also a research program. Um, I can type this up and send this to whoever wants it as well.
Yeah, yeah.
Yeah,
I want to
there's
speak briefly about the state fair as well, which is that some people, their public school or private school might have a science fair, and then the school endorses several of the participants in the school fair to go on to the regional fairs, and then the winners of the regional fairs go on to the state fair. And so that is a common track. But then there are some people, you go to school and maybe your school doesn't have a science fair, and we have several students who had that experience. And what you do under those cases is you apply either directly to the regional fair or directly to the state fair. And so all of these, in the case of Massachusetts, they all have different deadlines. And it is somewhat complicated because some of the contests for example, require you to have one form for your abstract, another form if you have any human subjects, another form to get approval for your overall plan. And so you do have to kind of like look at which contest you're applying to and discover what the deadlines are specific to that contest. That is something that we assist students with in the CSA 5 class. To be perfectly honest, it's mainly just like looking at the deadlines, contacting the different institutions, and getting the requisite paperwork. But that's something that if you don't take the class, you can also do yourself. Call these institutions and make sure that you file things on time. We try hard in the classes to make sure that the students file it so far in advance that if they get rejected for some reason or another, they have a chance to fix it and then resubmit. That's something I would recommend everyone should try to do. And the downside of these contests is that most of them are only yearly. So it's not like the USA Computing Olympiad where you can kind of like do it for like 4 times a year. So if you screw up one month, you can try like the next month. So a lot of these, like if you don't do the paperwork right, you miss the entire year. But they are cool contests because you get to go there, see a lot of other people who are doing really cool other projects, make some friends. It's usually an event as well that you can like just hang out and eat food at. And so
Also,
they're pretty
yeah,
fun.
another upside is once you come up with like a research project that you think is like significant or like beneficial, you can apply it to more than one science fair. Like you're not limited to just applying to one science fair. You can apply it to multiple science fair, and that really increases your chances, if anything. So that's another benefit.
Yep. Okay, so that pretty much concludes our talk, and it's 8 o'clock. If there's any other questions, feel free to type them now. We'll wait a couple minutes for anyone who has questions. I guess, yeah, I can fill in the time with talking about the core curriculum while people are asking questions. So I guess the core curriculum, which are these fundamentals and then CS classes, they're teaching. If you went to university and studied computer science, or if you go to a school and say like take like AP computer science, a lot of the concepts are the same, like variables, if statements, loops, arrays, functions, iteration, recursion, object-oriented or programming, polymorphism, and more or less in that order. And the classes in the core curriculum have the students build projects. Usually they do one kind of group demo every single week, and then they do some kind of independent project towards the end of the semester. Some of the classes, like these B classes, tend to have larger independent projects. Especially these orange classes and the red classes, they come with, and I mean, sorry, by red, I mean like the CSO2A and CSO2B. They also come with like a fairly frequent number of problem sets, which are like homework assignments they have to do every week. The lower level fundamentals classes have less required homework, but still some, and also some optional homework. But the basic idea is that it prepares students over the years to do the practice they need to really solidify these skills. We kind of compare it to like playing an instrument. You want to be good at scales, and you want to have good technicals in addition to having that creative and that breadth of applications, because if you don't have the technical capacity, then it'll be really a struggle oftentimes when you're trying to be creative. That's definitely the case with computer science. And so if when students are learning this stuff, it means that when they're doing the high level project, they're not worrying about how do I get data from this format to another, or how do I write this search algorithm or the sorting algorithm or whatever, and they can focus on the more advanced things. But we do it in a way that like they get to make video games or like audio programs or video programs or different kinds of like applications related to like science. And so it's not just homework assignments throughout the entire thing. Yeah, so that's the core curriculum that Robin, you were asking about, or it's Reuven, sorry. And the core curriculum is one semester for each of these classes. Usually students take them for like 18 weeks, and then they that's like usually like September to like January or something like that. Sometimes students take them over the summer. That's pretty rare, but like then it's like a 1 month compressed curriculum. And then these light color ones can sometimes be skipped, while the darker ones, we generally require students to go through them unless they have some outside experience, then they can kind of like jump into a later level. So that's like the main core curriculum. You can go onto the KTBYTE website and look at those classes. They're taught both in person and online, so you don't have to be based in Massachusetts to be taking any of these classes. And they all have classes starting in September right now. Some of them have classes starting in August, actually. But yeah. Yep, so that was that question. Jenny, did you have anything? Okay, okay, okay. Well, okay, so it's 8 o'clock. If there's no other questions, then I guess Pratik and I thank you all for attending.
Yep.
And
Thank you.
yeah, yeah, we'll send you guys all the material afterwards. I think we have everyone's emails, right? Yeah. So yeah, have a great rest of your evening, and hopefully you guys will take this interest and you know, try to learn more about this field on your own. Okay. Oh, we finally got another question. Um, if you already won silver for Yusuko, can you go to CS9-2? Yeah, yeah, that's not related to research, but yeah, I think we allow students who have placed in who have already placed in gold to attend CS9-2, meaning that they've already placed into gold, not placed into silver. If we have only placed into silver, we usually require them to take CS9-1. The USACO, this is not related to AI, but the USACO has changed significantly pretty much every year in the past 3 years. Starting with the creation of the new bronze level, the creation of the new platinum level, and then each year they've been tweaking the difficulties. Previously, 90 and 91 were very similar, just kind of like slightly more difficult versions of each other. But nowadays, 90 and 91 have pretty significantly different algorithms, and 91 and 92 have completely different algorithms in them. So we usually say that if you're supposed to be taking the 91 level and you take the 92 level, that might actually hurt you because you'll be prepping for algorithms that don't even show up in the other ones. We have a parent asking, what's the difference between Fund3 W, A, and B? W is week long, so it's short. There's usually no homework. A and B does have homework. A is usually for new students. These are done in processing. B is usually for continuing students who still aren't ready for the kind of the problem set intensity of CSOA. Because once you hit CSOA, it's kind of like paced at the high school level. You get like a full problem set, usually like 5 problems, sometimes 10 problems every week. And so, yeah, we usually say if you're like under the age of high school or you're like 12 or 13 years old, we try to have them go a little bit slower, especially if they're like 10 or 9 years old. Students benefit from not rushing too quickly and doing more projects and trying to get like really good marks in all of the different assignments before they go into OOA. But FunB is like a optional track based off of pacing. Yeah. But yeah, W has no homework. So all like the W's are like shifted left because a lot of them are just, even though they might cover the same material, they're just not as hard because it's only 1 week and there's no homework. So it's not easy to reinforce everything. Okay, so I think we're all set. And that'll be it. Okay, so we'll see you all later.